So I'll be talking about our recent work constraining cosmological parameters with strongly lensed gravitational wave events. The work is done in collaboration with Saswat and Ajit at ICTS and Jesse from UCSP. So gravitational waves are a completely new window onto the universe, and so far hundreds of GW signals from compact binary coalescence have been already detected, and we expect thousands of events to be detected within few years. And with 3G detectors like Cosmic Explorer and Einstein Telescope, we expect millions of GW events detection per year out to Redshift 15. So far most of the detected sources are the BBHS binary black holes. Gravitational lensing. So gravitational waves can be deflected while traveling to us by the intervening mass distribution, mostly by the galaxy and galaxy clusters. So the probability, the lensing probability is very small. It's of the order of 10 to the power minus 3. So 1 in 1000 events is expected to be lensed. So with 1000 GW detections, the first detection of lens signal is expected within few years. And with the 3G detectors, the Cosmic Explorer and Einstein Telescope, we'll have millions of GW detection per year. So that will lead to there are 1000 lens GW detection per year. So that then we'll have a completely new data set, and that will be a completely new probe to astrophysics and cosmology. So our work is probing the cosmological parameters using the time delay distributions of these strongly lensed GW events. So what is the motivation of our work? Some cosmological parameters are very well constant from the CMB at high redshift, Z of the order of 1000, and other astronomical observation probe the lower redshift, Z of the order of 1. So probing the intermediate redshift would be of considerable interest. By intermediate, I mean Z 1 to 15. So GW strong lensing could be one means of doing so. So the strong lensing of GW will produce multiple copies of signals that will arrive us at different times. So there will be a time delay between the lens signals, and this time delay can be accurately measured, and we can use this time delay distribution to infer the cosmological parameters. So the distribution, so from the distribution of time delay, this lensing time delays, we can constrain the cosmological parameters as it contains the imprint of the cosmological parameters. So the time delay, let's say we have a source at a redshift ZS and a lens at a redshift ZL, and the lens have a velocity dispersion, line of sight velocity dispersion sigma. Then the time delay between these two lens signal is given by these expressions. So this time delay depends on the this distance combination contains the cosmological parameters explicitly, and it also depends on the this lens redshift ZL. That means the time delay distribution will depend on the redshift distribution of the lenses, and also it will depends on the source redshift ZS. So the distribution also depend on the redshift distribution of the sources, and it also depends on the sigma. The sigma is the velocity dispersion of the lens, and it has a one-to-one relation with the mass of the lens. So it depends on the mass distribution of the lenses, and also this impact parameter y. So impact parameter should be less than 1. So this is the strong lensing condition to produce the multiple images. Now this ZL, the redshift distribution of the lenses, and this mass distribution of the lenses can be obtained from the halo mass functions. Halo are the concentrated region in our universe. So the halo mass function gives us basically the number counts of such objects in some mass range, let's say m to m plus dm. So if we have halo mass functions, we can obtain this mass distribution of the lenses and the redshift distribution of the lenses. Now for the source redshift distribution of the lenses, we can obtain by observation. So by the time 3G, we'll have millions of events detection. So we can very well constrain the source redshift distributions. So from that, we can obtain the time delay distribution. So the time delay distribution contains the three independent things. The first thing is the cosmological parameters, and second thing is the halo mass function, and the third thing is the redshift distribution of the sources. So we want to infer the cosmological parameters, so we must have the knowledge of the halo mass functions and the source redshift distribution. So this is the imprint of the cosmological parameters on the time delay distributions. So the plot on the left hand side shows that if we increase the matter content of the matter density of the universe, then the time delay distribution shifts towards the right. And on the right hand side plot, if we increase this Hubble constant, then the time delay distribution shifts towards the left. So by seeing it, the variations looks very small, but in Bayesian analysis, it will be able to put stronger constant on the omega m and h naught. So to plot, given a value of cosmological parameter omega m and h naught, we will be able to construct these time delay distributions given the Helmholtz functions and some source redshift distribution. So there are few Helmholtz functions; those are theoretically motivated and from the in-body simulations. So for this time delay distributions, we have assumed the Helmholtz functions, and we call these constructed time delay distribution as template time delay distributions. And we will use this time delay distribution to infer the cosmology from the observed data. So now let's say we have n confirmed lensed BVH merger detections. So we will have n number of time delays. So this set of time delay is our data. And we ask the question, given this set of time delays, what is the value of these cosmological parameters? So the left-hand side of this equations is the constant quantity. And so on the right-hand side, this P omega is the prior. So it's the prior knowledge we have about the cosmological parameters. And the likelihood is P of this delta Ti given the cosmological parameters. So this we call likelihood, and it can be obtained from the template time delay distributions. So far no confirmed lensed event detection. So we need to simulate the lensed events. So we simulate, let's say 50,000 lensed events, assuming some true cosmological parameters. We call it true cosmological parameters. So for our simulation, I have assumed the cosmological parameter values of this omega m as 0.316 and h naught as 67.3. And also we need to assume some Helmholtz functions. Let's say and we assume some Helmholtz functions, Helmholtz functions. And assuming that we simulate 50,000 lensed event, and from this, and we will use this as our data set, and from this data set we try to infer the cosmological parameters. So assuming the independent measurements, so this likelihood can be written as a multiplication of these individual measurements. Now this is the result. So this is the expected precision on the measuring cosmological parameters. So this orange one is the from GW lensing with from 50K samples, and this or the blue one shows the Planck result, and these contours are basically the 67% and the 95% interval. So we see that the true cosmological parameters are 0.316 and h naught is 67.3, and we have recovered that 0.318 and 67.9 is some error bars. So the accuracy in the precision from the GW lensing on the omega m is 3.7% and h naught is 2.9%. So to compare it with the Planck measurements, and so I have plotted the Planck posture on top of our result. So the Planck accuracy is much better. So, but the noticeable thing is that the direction of the correlations of these parameters from the Planck measurement and the GW lensing measurements are not in the same direction. So we can use this Planck measurement as a Bayesian prior in our analysis to improve the constant on the cosmological parameters. So here I have shown that if we don't have 50K lensed event detections, if we have 20K or 10K detections, so basically in this plot is showing that with the increasing number of events, we will have the better recovery and also the better precision. Yeah. So as you have seen that these correlation directions are different from the Planck measurement. So the plot on the right hand side shows that if we use the Planck measurement as a Bayesian prior in our analysis, then we see that this the precision on the omega m and h naught has been significantly improved. So we can use the CMB measurement as a prior and improve the constant on the cosmological parameters. Now, so as I have said that this time delay is a function of several things. One of the important thing is this Helmholtz function. So to simulate the data, we have used some Helmholtz functions, let's say Helmholtz functions, and we have recovered it with some template distributions. And to construct these template distributions, we have assumed there are some Helmholtz functions. Now let's say in the simulations, we have assumed this Helmholtz functions, and in the template distribution construction, also there is a used Helmholtz function, this BB, then everything is fine. The true cosmology is recovered within 67% and the precisions are all good. Now if we construct this template distribution with some another different Helmholtz functions called Jenkins, then we have seen this blue contour. The true cosmology is outside the 95% interval. So this true cosmology is not recovered. So this shows that the time delay distribution is a very strong function of the Hello mass function. So we need to have the accurate knowledge of Hello mass function to infer the cosmological parameters accurately.
Souvik, you have 5 more minutes.
So I'll summarize the results. So with the 50K lens BBH events, we'll have 2.9% precision on the H0 and 3.7% precision on the omega M0. And if we use Planck as a prior, the precision has increased significantly, 0.4% for H0 and 1.2% for omega M0. And also this H0 can be very well probed from other lower redshift probes. So if we assume some value of H0, then only from GW lensing, we will have 2.2% precision on the omega M0, and that is comparable with Planck measurements. And so as we have seen, this time delay distribution is a very strong function of the Hello mass functions. So we can flip the problem, fix cosmology or acquire the properties of the lenses. That will be a direct probe towards the Hello mass functions, or constrain the both cosmology and the Hello mass functions. So this work is in progress. So yeah, I'll stop here. Thank you.
Thank you, Souvik, for your talk. Now we will have a couple of questions.
Yeah, some really basic questions. So I was just trying to understand this time delay. So let's say you have a source and then this lens, and then you are looking somewhere. So of course, this time delay will depend on like how are you placed symmetrically. So is that so is that something you assume that you're kind of placed symmetrically with respect to the source?
No. We have not assumed this Y parameters. So this Y parameter can be 0 to 1. So it is a dimensionless parameter. So the source can be anywhere. And also,
so where is the? So then it looks like the time delay can be vary by a huge amount, right? Depending on how.
Yes. So you can see this time delay. Actually, this is the log of the time delay. You can see. So it can be go to the months and 2 years.
So this distribution is with respect to variation of what?
The variation, the lenses can be anywhere. The lenses can be in between this.
Varying the position of the lens, and then you plot this distribution.
The lenses can be anywhere in between these, also anywhere spatially. So these are the.
Okay. And so the other question is, so people have observed signals which are coming at different times, and they know that it's because of lensing. Has it already been
electromagnetic observations, they see different images of some quasars, but in GW there is no confirmed lens detection yet.
Okay.
Other questions?
Yeah. Yes. Hello. No. Oh. Can I ask? Maybe I missed it, but this 10 to the -3 figure, which right at the beginning that you showed the fraction of events that might, this lensing problem, roughly where does that come from?
So we actually calculate this probability. So for the strong lensing condition, the source need to be within the Einstein radius or the influential region of the lenses. And we calculate this using along the line of sight. So what is the probability that it will encounter a lens while traveling? So I can show the expressions. So it also depends on the cosmology and the Hello mass functions, all those things. Oh, sorry. Yeah, so we will be able to calculate all those things, and we calculate the differential optical depth, it calls. So it depends on the redshift, and it depends on the Hello mass number density of the lenses and the cosmological parameters also. So in detail we can calculate, and this is a rough estimations. We simulate all those things, and we see that from the millions events, the lens events are thousands. So that's why I'm saying that it is 10 to the power -3.
Okay, any more?
Yeah, Souvik, I have a very basic question. So how exactly do you determine this Hello mass function? It depends on the theory you would take, and
so there is that's the actually these Hello mass functions are not well probed in the except in the low redshift. So, and also some are the theoretically motivated, like the first one is space sector and all those things, and some are from the n-body simulations, but there are some huge error bar on these Hello mass functions.
So also, does it depend on what omega m and omega lambda?
Yes.
So
it has also dependent on the omega m and.
So that you would give as input from the Planck data, or what?
Yeah, I'm including those effects also.
Yeah, thank you. Yeah, Souvik.
Can you hear me?
Yeah.
Okay, so I have a question regarding your. Okay, so the question is regarding that correlation graph. One is using your lensing, yeah, and the other one is using this, I think, Planck 2018. So why this correlation like is in opposite direction?
So it's because of the we are probing through the our observable. Our observable is the time delay distribution. So it acts differently when we increase the omega m and increase the h naught. And for the CME measurements, they observe some temperature power spectrum. So they have a different kind of behavior or the variations with these cosmological parameters. So that will determine and the correlation of these parameters. So it's the observable we are probing.
Thanks.
Okay, so let's thank Souvik for his interesting talk.